In August 2017, a petrochemical refinery shut down hard. Its safety controllers, the systems whose only job is to slam the process to a stop before anyone gets hurt, had fired an emergency shutdown on their own. It had happened once before, that June. The operators wrote it off as a glitch and restarted. This time, the shutdown was serious enough to bring in outside investigators, and when they pulled the safety controllers apart, they found something no one had ever reported finding before. Malware. Not in the computers that run the plant. In the one system built to keep a catastrophe from happening. That system has a name, a safety instrumented system. Its only job is to watch for dangerous conditions and trigger a safe shutdown before they turn into a disaster. Every serious refinery, petrochemical plant, and gas terminal has one. It is the last automated line of defense between a process going wrong and people getting killed. Triton, also called TRISIS, also called HatMan, 3 names from 3 teams for the same code, was the first publicly known malware ever built to attack one. Its authors did not want to steal data or hold files for ransom. They wanted to reach inside that last line of defense, switch it off without anyone noticing, and leave it looking perfectly healthy. This is how they got in, what they built, and the accident that stopped them. To see why Triton was different from everything before it, you have to understand the system it attacked. At any serious industrial site, there are 2 separate control systems, and engineering standards require them to stay separate. The first runs the plant. Engineers call it the basic process control system. It manages temperatures, pressures, and flows, making the constant adjustments that keep a process inside its safe envelope. This is the layer where the controllers live, where the distributed control system lives, where the operators get their readings. The second watches the first. It is the safety instrumented system, and almost all of the time, it does nothing. It monitors the same process, with its own independent sensors, its own wiring, its own logic. And if something goes wrong, that the control system fails to catch, it shuts the plant down, automatically and safely. It is not there to run the process. It is there to stop it. The international standard IEC 61511 spells out why the 2 must stay independent. If the control system fails or is compromised, the safety system has to remain untouched. Share the same sensors, the same logic, the same network, and a single failure can take both at once. A safety system is only worth something if it is independent of the very thing it is guarding. Below it sits one more layer that needs no computer at all. Mechanical relief valves and rupture disks, the purely physical last resort. So the safety system is the last automated line of defense, not the last line of any kind. Triton targeted a Schneider Electric safety controller called the Triconex Triton, one of the most trusted SIS platforms in heavy industry, thanks to a design feature called triple modular redundancy. Inside the chassis sit 3 independent processors, each running the same safety logic, each reading its own sensors. On every cycle, they compare results and vote. If one disagrees, it is overruled 2 to 1. If the disagreement is serious, the whole system trips to a safe state, because in a safety system, uncertainty is worse than an unnecessary stop. That voting was built to survive hardware failure, a glitching board, a drifting sensor. It was never designed for the case where all 3 processors run the same malicious code, agree perfectly, and execute an attack that the voter sees as flawless consensus. That gap is exactly what Triton was built for. Triton did not appear overnight. Investigators traced the intruders back onto the facility's corporate IT network as far as 2014, about 3 years before they reached the safety controllers. The likely way in was a spear phishing email, one targeted message, one stolen credential, one foothold. Then they waited and moved using ordinary hacking tools across the corporate network, switching to custom backdoors as they neared the boundary with the industrial systems to stay below the radar of anything defenders knew how to spot. That boundary, the firewall between corporate IT and the operational network, was supposed to keep the two worlds apart. In practice, enough connectivity slipped through for the attackers to pivot across it, onto the operational network, and from there, onto the engineering workstation wired to the safety instrumented system. That last fact is the heart of it. The safety network at this plant was not air-gapped. IEC 61511 demands that the safety system be independent of the control system. But here, that independence stopped at the hardware and never reached the network. The workstation, used to program the safety controllers, could be reached, hop by hop, all the way back from corporate IT. And once an attacker is on that workstation, the Triconex offers something startling. Anyone on the network can program it. The Triton is programmed over a proprietary Schneider protocol called TriStation, running over UDP on port 1502. It has no authentication, no password, no key, nothing. Reach the controller over the network, speak the protocol, and it does what you tell it. TriStation was never documented publicly. The attackers reverse engineered it from the legitimate engineering software, and their custom version matched 202 of the 220 internal command names. That is months of patient work. One thing more was in their favor. Each Triconex has a physical key switch, with positions for run, program, remote, and stop. In program mode, it accepts new logic and direct memory writes over TriStation. In run mode, those writes are refused. At this plant, the key switches had been left in program mode during normal operation, exactly what Schneider's own security guidance warns against, but convenient, because it spared engineers a trip to the panel for every change. Convenience had become habit. An unauthenticated protocol, reachable from a workstation, with the key switch already turned to accept code. The door was open. What landed on the safety controllers was not a single program. It was a toolkit in 3 stages. The first stage was the delivery tool, a file called trilog.exe, a Python program compiled to look like a harmless Triconex log viewer. The sort of thing a maintenance engineer might run without a second thought. Its job was to open the TriStation connection and push the next 2 pieces. The second stage was inject.bin, an installer. It exploited 2 genuine 0-day vulnerabilities in the Triconex firmware, flaws Schneider did not yet know existed, and that would not be assigned formal vulnerability numbers until the following year. One let the malware write into protected controller memory it should never have been able to touch. The other escalated it to supervisor-level control inside the firmware. Crucially, these were holes in the firmware, not in TriStation. The protocol itself needed no exploit at all, because it had no security to break. The third stage was the implant, imain.bin, written in the controller's own PowerPC machine code. It buried itself in the firmware by hijacking a routine diagnostic command, so that every time the controller answered what looked like a harmless status request, it was really running the attacker's code. The implant gave its operators read, write, and execute access to the safety controller's memory. And from that point on, the key switch no longer mattered. The implant lived beneath it. Run mode could no longer lock it out. Piecing it together afterward, investigators found something larger. Both the safety system and the plant's main control system, the DCS, had been compromised. The attackers held both at once. That combination is what makes the intent so chilling, and it points to a two-stage plan. Drive the process toward a dangerous condition using the control system, while the silent safety system fails to fire the shutdown that would stop it. At a petrochemical plant, that ending is fire, explosion, or a toxic release. No such payload was ever recovered, so the final goal stays an inference. But the architecture for it was in place. None of it happened, and the reason is almost absurd. The malware had a bug. In August 2017, a flaw in the installer left the three redundant processors holding slightly different code. On their next comparison, they disagreed, and the Triconex did exactly what it is designed to do when its processors do not agree. It declared a fault and tripped to a safe state. At least 6 safety controllers shut down, and the plant went with them. The same thing had happened that June. That time, it was written off as mechanical. The August trip was bad enough to trigger the investigation that found the malware. So the voting architecture did catch Triton, but not because it detected an attack. It caught a code inconsistency, the same kind of glitch it would flag in a failing processor. Had the attackers written cleaner code, identical across all 3 processors, so the comparison passed, the voter would have seen perfect agreement and done nothing. Triton was not exposed by a defense. It was exposed by its own author's mistake. Triton was disclosed in December 2017, months after the August shutdown, by 2 firms at once: Dragos, which named it TRISIS, and FireEye, which named it Triton. The United States government's Industrial Incident Team analyzed the same code and called it HatMan. 3 names, 1 piece of malware. Attribution came later and carefully. In 2018, FireEye assessed with high confidence that the operators were supported by a Russian state research institute in Moscow, the Central Scientific Research Institute of Chemistry and Mechanics, known by its acronym TSENIECM. But FireEye was explicit. It judged the institute had most likely built the tools and said plainly that it did not have proof. In 2020, the US Treasury sanctioned the institute. In 2022, the Department of Justice indicted one of its programmers, Yevgeny Gladkik. An indictment is a charge, not a conviction, and no conviction exists. These are formal government findings. They are not the same thing as proof. One correction is worth making because it sets up where this series goes next. The group behind Triton is not Sandworm. Sandworm is a Russian military intelligence unit, the one behind the attacks on Ukraine's power grid. Triton came from a different Russian organization entirely. The 2 were sanctioned and indicted on the same day in 2020 for separate campaigns. A phrase followed Triton through the press: the world's most murderous malware. It is worth being precise. No one died. The attack failed before it could do any harm. What made Triton singular was its target, the last automated barrier between a runaway process and a catastrophe. But Mandiant rated the attacker's intent to cause physical destruction at only moderate confidence, and the malware itself killed no one and wrecked nothing. Designed to kill is a journalist's inference, not a finding in any technical or legal record. The group did not stop. By 2019, the same actor, tracked as Xenotime, was probing electric utilities in the United States and the Asia Pacific, scanning, mapping networks, testing credentials. No confirmed break-in followed, and US agencies later reported no evidence of any deliberate disruption of American energy infrastructure. The reconnaissance was real. The line it has not been shown to cross, so far, is intrusion. So what does a control room take away from this? 3 things. First, independence has to reach the network, not just the hardware. IEC 61511 requires the safety system to be independent of the control system. But independence inside the chassis means nothing if the workstation that programs it can be reached from corporate IT. At this plant, the safety system was its own island in every way, except the one that mattered. A safety layer is only as independent as its weakest connection. And here, that connection was a single workstation. Second, redundancy is not security. Triple modular redundancy is superb at catching a failed processor. It is blind to identical malicious code running on all 3 at once, because that looks exactly like agreement. As we saw, it caught Triton only by accident, through the attacker's own bug, not through any ability to recognize an attack. A cleaner implant would have passed the vote in silence. Third, the safety layer is now a target, and that changes the threat model. Stuxnet went after the process and left the safety systems alone. It needed the plant to look normal. Triton's authors drew the opposite lesson. If you want a process to run past its limits unchecked, the safety system is not something to avoid. It is the thing to disable first. A plant where both the control system and the safety system are under one attacker's hand has had its layered defenses collapsed toward a single point. Mechanical relief valves still sit below as a last physical resort, but counting on them is counting on the very catastrophe the safety system exists to prevent. Stuxnet attacked the process and left the safety systems running. And it worked in part because those systems did their job and never tripped. Triton's authors concluded that a safety system you want to defeat is not something to leave alone. That step, from sabotaging the process to disabling the protection itself, is the most dangerous line any industrial malware has crossed. Not because of what it did at one refinery in 2017, but because of the blueprint it left for whoever comes next. Next time, we move to a different country and a different kind of infrastructure. The 2016 cyber attack on Ukraine's power grid and the malware called Indestroyer. Stuxnet needed careful engineering to wreck one specific machine. Triton went after the safety layer. Indestroyer did something else again. It spoke the substation's own language and switched off part of Ukraine's capital, with no human at the controls. If you want to understand the machines that run the world and the moments they fail, subscribe.